Hi everyone, I'm Luca and I'm going to present wrong answers for wrong reasons, the risks of ad hoc instruments. Now let's talk a little bit at how we evaluate a teaching intervention. Now we all know that there are a lot of ways in which one can evaluate a teaching intervention. You might use some qualitative approach, maybe do some observational study, or you might want to do some more qualitative work, such as running a randomized controlled trial. Now let's narrow down a little bit this question and think at one possible way to evaluate a teaching intervention if you plan to use a randomized controlled trial. You take a group of people, participants, and you split them into two subgroups, a control group and a treatment group, to which you apply your teaching intervention and you hope to find some difference with respect to the baseline. Now, you probably want to run a pre-test with both groups to check that they are equal before the teaching intervention, so there is no difference among them. And you might want to carry out a post-test after that, and you hope that there is a difference between the two conditions. Now, we wanted to evaluate two modalities to teach expressions in the Java programming language. And for that, we ran an experiment in two courses. In one course, we divided participants into two groups, one that used a textual modality to learn about Java expressions, and the other one who used a graphic modality. We ran a pre-test for both groups and we found no difference. After the teaching intervention, we ran a post-test and we still found no difference between the two groups. We repeat the experiment in another course, the same two conditions, modalities to teach Java expressions. Again, no difference in the two groups in the pre-test, but this time we found out that there is a difference in the post-test. Now, what would be your explanation for this difference in the outcome? You might think that the difference relies in the population being different, but that's actually not the case. These are exactly the same population. You might be wondering why there is a difference in the post-test. Let's dig a little bit and try to understand better how to evaluate a teaching intervention for real this time. Well, the first step you probably need to do is to recruit participants. And now there is a question on how many participants you need to show that there is a difference. Let's take a look at this in depth. We carried out a literature survey considering papers at 3 major computer science education conferences in the last 5 years containing the words post-test or post-test with a dash to include experiments. We found out that in the slight majority of papers, n is less than 30 per condition. For this reason, even being at a small university, we're able to recruit 21 students in one group and 19 students in the other group. Then we designed a teaching intervention, and we won't delve into the details here because we all know what's our teaching intervention. Finally, we need to choose an instrument. And we know that there exist 2 categories of instruments. We have standardized instruments, such as concept inventories, and we have ad hoc instruments, so instruments that have been specifically designed for an experiment. Now, standardized instruments should be preferred for their reliability, their validity, and because they afford comparisons across studies. If one uses the same instruments across multiple studies, then some meta-comparisons can be carried out. However, we should also be aware that 2 dimensions exist in terms of scope and density. Now, the scope of an instrument can be narrow if the instrument targets, for example, variables, or it can be wide if the instrument targets, for example, all the skills in imperative programming. And the separate dimension is the density of the instrument. The density might be low, so given a scope, it targets just some areas in that scope, or it can be high. Given a scope, it targets almost everything that needs to be in there. scope and density together determine the duration of an instrument. Here is an image that shows how scope and density determine duration. Each dot in the image is a question that your instrument might contain, and you see that we have quite a lot of differences. You might have instruments that are very short, low density and narrow scope, and instruments that are very long, high density and narrow scope. But when we look at the instruments that are out there, we see that usually concept inventories tend to fall in the low density wide scope because they want to be generally useful. Whereas when you design an instrument specifically for an experiment, you want to cover very well, so with high density, a relatively narrow area. And that's what we usually want. And it's a reason, probably because, and that's one reason that makes people favor ad hoc instruments. Now, in the same literature survey, we looked at papers at the same 3 major conferences, and we found out that 94% of them use ad hoc instruments or course assessments. So everybody seems to develop their own ad hoc instruments for the experiments. So this choice of choosing an instrument boils down to design our own instrument. Now, there are different ways in which one can ask questions in an instrument. One popular one is multiple choice questions. We investigated that in the same literature survey, and we found out that 65% of ad hoc instruments include multiple choice questions. And so that's a pretty popular way to assess knowledge. So the design an instrument turns out to be a design a multiple choice question instrument. Finally, with our teaching intervention and our multiple choice questions, we run the experiment, and we need then to analyze the data that come out of multiple choice questions. And here's an interesting part. Now, the process of analyzing multiple choice questions can be quite interesting, but let's start with a simple way to analyze them. The first part is to decide a scoring scheme. For example, you might decide to award 1 point when the multiple choice question is correct, or 0 points when it's wrong. Then you assess the correctness of the answers in the pre and post test and assign points. And finally, you would want to compute the statistics and see where there is a statistically significant difference. We did this in our experiment in which we wanted to investigate the 2 modalities to teach Java expressions, analyzing multiple choice questions in the simple way, and we found out that there is no difference in the post-test between the 2 modalities. But then, if one really thinks at what happens in the real world when you administer a multiple choice question instrument, you are confronted with the reality that the real world is messy. For example, what about missing answers? What do you do in your scoring scheme? What's the threshold to decide to discard a participant for too many missing answers? Or when you decide the correctness of answers, are you really confident that you're assessing the right thing, that you are really assessing whether the student knows something? Well, one way to tackle this is to ask for explanations. And that's what we did in our experiment. We augmented each multiple choice question with a free text explanation. And then we decided a scoring scheme for those multiple choice question explanations. So if one just looks at multiple choice questions, you can divide it into 3 categories: correct ones, wrong ones, and missing ones. And if you just look at the explanation, you can roughly divide it into 4 categories: correct ones, 2 imprecise ones, clearly wrong ones, and missing ones. The cross product of these 3 times 4 categories yields 12 different possibilities. We'll now investigate a little bit these possibilities because some of them are really interesting, and I want to show you some examples from our experiment. The first category is when the multiple choice question is correct and the explanation is correct. This means that everything is fine, and we award a correct category. Even when the explanation is somewhat imprecise, we decide to leave the correct category. But when the multiple choice question is correct, but the explanation is clearly wrong, there is really something wrong, and we call this category bad explanation. Let's take a look at an example taken from our experiment. Here is a simple demo class with one static method, and we ask the students this multiple choice question. What happens when we compile this class and we execute the method demo.run? And the three possible options were that the code successfully executes, or there is a compilation error, or there is a runtime error. Now, for the category that the multiple choice question is correct, but the explanation is wrong, this is the correct multiple choice question. There is a compilation error, but these are three instances of explanations that students actually wrote that show that they really do not understand this. The first one is that you can't use the minus inside the print line. The second one is that plus current text is invalid. And the third one is that you cannot compute operations inside the system.out.println. Okay, back to our table. We finished the multiple choice correct column by saying that when there is no explanation, we assign it to a specific category, no explanation. Then for the multiple choice wrong column, we might have the case in which the explanation is indeed correct. This is actually surprising, and so we might want to dive in and have a look at an example. Here is the same exercise, is the same question as shown before. The student in this case selected the first item, so the code successfully executes, which is wrong, but then wrote this perfect explanation that shows that he probably understands. Since there is a string in the print statement first, everything after it will be handled as a string. Therefore, the only operator valid is plus to concatenate strings. We fill the rest of the column for wrong multiple choice questions with wrong. And finally, when there is a missing multiple choice question, but there is a correct, clearly correct explanation, we say that this is a proper explanation, and in all the other cases that something is wrong. Now, it's just a matter of deciding how many points you want to award to each one of these blue categories to reach a more correct assessment of students' understanding. So, back to our experiment to evaluate two modalities to teach Java expressions. We have that these are two different post-test outcomes, and they are exclusively determined by the way we analyze multiple choice question. In the left one, we analyzed multiple choice question the simple way. On the right one, we also accounted for explanation, meaning that we triangulated the answers to multiple choice question with the explanations according to the table I showed you before. So here's the main takeaway from this. You should always question the reliability and the validity of the instrument you use. You should always prefer standardized instruments, and if that's not really possible and you need to develop an ad hoc instrument and you choose to use multiple choice question, you should really ask for explanation. Otherwise, you really risk to incur in unwanted outcomes. Here is a summary of what we did. The ad hoc instrument is published at this URL in Zenodo so that it's publicly accessible and you can reproduce the statistics documented in this paper. And I'm now happy to take any questions you might have.